All right, for those of you that are on Zoom, looks like you've already typed something into the chat, so I'll just make sure. Yep, everybody's just telling me that they're here. I'm going to float the roll sheet around for the people that are here, and then we'll get cracking on further current mirror discussions. All right, so we are going to begin today. Let's just see other people saying here. Yep. All right, we are going to begin today by discussing the Npn Bjt Current Mirror. So as we discussed briefly at the end of Wednesday's lecture, a current mirror really contains two parts. There's a part that senses a reference current, and then there's a part that copies the reference current, right? So if we have some reference current flowing into our black box, as it were. Let's see, 37. Go away. Like so. And then we're going to have some copy current right here. So let's start with, I guess, what would be the easier part of understanding what's going on with this guy, right? So everything in the blue box is a black box device right now that is sensing that current IREF and then providing a copy of it to the output terminal on the right. So since we're talking about BJT current mirrors, it's probably fairly obvious that we are going to create that copy current by using a BJT current source. So that would look something like this. People showing up late. And I'm going to call this guy Q1. All right. So Q1 is providing I copy from some sort of internal black box device. We're not entirely sure what that is yet, so we're going to figure things out. All right. So I'm going to call this guy node X with some voltage Vx that is exactly equal to VBE, right? And so what we can say right now is that our sense stage must be taking IREF as an input, and it must be outputting that voltage Vx is exactly equal to VBE to the base pin of transistor Q1 in order to make I copy equal to IREF. So transistor Q1 is going to carry a current, or ideally is going to carry a current of IS1 times exp of Vx divided by Vt, and this should be equal to IREF. And so we can rearrange this guy and see that our output voltage Vx must satisfy the relationship of Vt natural log of Iref over IS1. A circuit that follows this specific voltage relationship where Iref is the input and Vx is the output is simply a diode connected transistor. So I can erase this black box right here and say instead that we're going to have something that looks like this. Qref where we are tying our collector to our base, okay? And this is a current mirror, meaning that Iref is pretty close to iCopy under the specific condition that ISRef is absolutely equal to IS1, which means transistor Q1 has to be identical to transistor Qref. Okay? So this is our basic current mirror, but there are two important caveats that we need to consider. The first is that we have, to this point, completely neglected any impacts that base currents may have, right? And so what I mean by that is because our base current for a BJT transistor is non-zero, we are going to observe that Iref splits up in some shape or fashion. And some portion of it will flow through the collector of Qref, and then some portion of it will flow through the bases of both Qref and Q1, right? And if we wanted to make multiple copies of our reference current, some portion of that reference current is going to break off and flow through all those other bases as well, which is going to introduce more and more error into our copy currents the more and more times we copy it. Okay, so that's something that we're going to have to pay attention to. We can observe pretty easily here. Let's call this current right here IC ref has to be the exact same thing as IC1, because if both of them have the both of these transistors have the exact same base emitter voltages, then they have to both be carrying the exact same amount of collector current, right? So that's another thing that we can observe. One final thing that we can observe is it is possible for that voltage Vx to vary with temperature, but that will not cause variations in the copy current, right? So if Iref is supplied by a very stable temperature insensitive current source, like we discussed at the end of Wednesday's lecture, Qref and Q1 aren't particularly temperature insensitive devices. So we might see that that voltage Vx rises or falls to accommodate a change in temperature, but because Iref is temperature insensitive, iCopy has to be temperature sensitive as well. So Vx can move around as much as it needs to keep supplying a constant current of iCopy to all of the copy transistors. Does that make sense? Okay. All right, so let's talk about duplicating iCopy, because if we only needed to make one copy of our reference current, then what would be the point of making a copy of it at all? We would just connect our good reference current to it to begin with. So we can copy things by simply connecting more BJTs to node Vx. So that's going to look something like this. Here we have our reference. Here we have some transistor Q1 carrying a copy current. Let's call it I copy 1. That is not a Y. Good God, no. And then we might have another copy current, I copy 2. And so the only connections that is made here, and this is a shorthand notation way of drawing it to make things less ugly, is that we're just connecting all those bases together. So when we're going to be doing KVL in a couple of minutes, I want to be very clear here. We have some base current IB1, and then another base current IB2. And then if we copied it again, say, like so, we have I copy N, where this guy is Q2, this guy is Qn, and here's our base current IBN. Our reference current, IREF, is supplying IB1 plus IB2 plus IBN, etc. So we don't say that IB1 is splitting off to provide IB2. Those are all leaving the exact same node. I'm just drawing a shorthand notation representation. I just want that to be real clear. All right. So we can make a bunch of copies of the exact same current value, which is useful, but it's probably more useful for us to be able to scale up our copies. Meaning if we have a reference current of, so let's say 1 milliamp, what if we wanted to make a current somewhere else be 2 milliamps? Anybody have any thoughts on how we might do that? Copy it twice and then tie them together. Okay, so we can connect transistors in parallel to generate larger versions of our copy current. So if we have a situation like this guy, where we have VCC, here's our reference current, here's Qref, Q1, Q2, Q3, Qn, let's say, sorry. This guy here, I copy, is going to be approximately equal to N, the number of transistors that we have connected in parallel, times our reference current. Seems fairly straightforward. What if we want to make copies of a current that's slightly smaller than our reference current? So like some fraction of our reference current. What do you think we need to do there? Yeah, do it the other way. So instead of putting all of our copy currents in parallel, we're going to make reference transistors in parallel. So that would be something like this. Oh, correctly. Here is QREF-N, QREF2, QREF1. And then we can tie that to some copy transistor Q1 such that I copy in this case is approximately equal to 1 divided by N multiplied by IREF. So if we wanted a specific ratio like 4/5 of IREF, we would copy QREF 5 times, copy Q1 4 times, and that would give us the ratio of 4/5 multiplied by our reference current. So why does this work? Let's start with something fairly reasonable question. Recall that IS, the saturation current, is equal to AE, the emitter area, by Q dN Ni squared divided by NB, the base biasing, or excuse me, the base dopant concentration, divided by WB, the width of the base. When we are putting transistors in parallel, all we are doing is scaling that factor AE. We're making it look like the area of the emitter is larger. That's all we're doing. So another shorthand notation of doing this without having to draw 30 transistors in parallel or whatever would be something like this. So I'm going to call this M multiplied by AE. And over here, our copy might be N multiplied by AE. We would see that I copy is simply N over M IRF, with some error that we're about to have to take into account. QREF and Q1. So I'm just scaling the emitter area of QREF by making M copies of it. I'm scaling the emitter area of Q1 by making N copies of that. And then when we find out that our I copy then is simply N divided by M multiplied by our reference current. So we can get practically any current that we would possibly want from a single reference current using this type of scaling. Okay.
So it's just, so I think this goes, could you get the same effect of using, like combining multiple copies, basically changing your copy, if you just change the areas of the
Yes, if you were to physically change the, like in the design process, if you were to physically change the areas, sure. But typically speaking, you don't really have a whole heck of a lot of control over that. Right. So this is a way of effectively doing that in specific configurations to get the currents that you want. All right, so now since we've made some number of copies, it's probably time to start introducing the error that is associated with copying our current over and over and over again. And I want to say something real quick here. The book effectively kind of gives you an equation that seems like an end-all be-all answer, but that's not remotely true. The process behind where that equation came from is really how you wind up determining the error. And I'm going to work an example problem that kind of shows you that in a minute. So with that in mind, I want this thing scroll, there we go. I'm going to look at something fairly simple. We have some reference current, IRef, being sensed by transistor QRef. And we have one emitter area in QRef. So we're not scaling down our reference current at all. All right. And then let's look at if we have a copy transistor that has an area of n emitter areas. Like so. So when our reference current enters node X, we'll call it, we can see that some of it is going to branch off and flow down in this way. So we're going to call this guy IC ref. Some of it is going to branch off and flow through here. And so this would be IC ref over beta, right? And then this guy right here is going to be the base current of transistor Q1, where Q1 is carrying a current, collector current of, let's call it IC1. So let's say that right here we have IC1 over beta, right? So if we apply KCL at node X, we get that I reference is equal to IC ref plus IC ref over beta. Dang it, I gotta save it and restart. Plus IC1 over beta, right? So things are looking a little. However, we can recognize that since QRef and Q1 have the exact same base emitter voltage, that means that IC ref, by definition, is 1 over n times I copy. And so if we put that in, or I copy or IC1, however we want to write it. So if we put that in, we get I ref is equal to I copy over n plus I copy over n beta So I'm replacing IC ref with, okay, yeah, so I copy over N beta plus I copy over beta. Get my other page out of the way. We can factor out so this would be, let's see, 1 over N plus 1 over N beta plus 1 over beta. And if we rearrange this guy, we find that I copy is equal to N times I reference divided by 1 plus 1 over beta times N plus 1. Where that denominator term here, or actually just the 1 over beta times N plus 1, is telling us how much error we're introducing, right? Because it's making our copy current smaller than I reference, or N times I reference, which is what we would expect if our base currents were neglected. So this can be a considerable problem if N is very large. I mean, I don't know how many copy currents are required in, say, our cell phones or anything like that, but my best guess is it's a crap load, okay? Like probably tens to hundreds of copy currents all over the place, biasing different things. Now, really, your phones are working on a MOSFET technology, not BJT technology, but just imagine a large scale microelectronic device. We can see that it's pretty easy to introduce an awful lot of error pretty quickly. So we can actually do something here to correct this. And it is a fairly elegant solution. We place an emitter follower into our circuit that is going to supply those base currents. So if we make one reasonably small modification, here's IREF. Here's QREF, same emitter area AE. Now, we put in a transistor here, QF. And then over here is our copy stage, NAE. This guy is Q1. What that is doing is having this guy, we're calling it an emitter follower because we're applying an input signal at the base, and we're taking the output at the emitter. So that emitter follower is now responsible for supplying the base currents instead of IREF. That's going to give us a significant reduction in the error that we see. So I'm gonna list a couple of currents here so we can see what's what. So let's call this guy IC ref. Let's call this guy IEF because it's the emitter current of transistor F. This guy is ICF, making this guy IBF. This guy is going to be I copy over N beta because we are still working under the assumption here that IC1 will be approximately equal to IC ref. which means this guy right here is I copy over beta. I'm going to call this node X and this node Y. And the other assumption that we're going to make is that ICF is approximately equal to IEF, meaning our collector current through our emitter follower, because this is totally a BJT, is roughly equal to the emitter current, which will be true most of the time, right? We're not making tons and tons of copies of this guy, so this is effectively the same thing as saying when we only have a few copies, it doesn't matter. Got the exact same thing going on here. So if we do KCL at node X, this tells us that ICF is equal to I copy over N beta plus I copy over beta, which looks like, thing will write. Still not writing. There we go. I copy over beta times 1 plus 1 over N, which means our base current, IBF, is ICF over beta, which means we would have I copy over beta squared times 1 plus 1 over N. When we do KCL at node Y, we have IREF is equal to ICREF plus IBF which is simply I copy over N sorry, I made a mistake right here. IC1 should be N ICREF because we're scaling the emitter area of our copy transistor. So I just forgot to factor an N there, writing stuff down. So I apologize for that. So I copy N plus I copy over beta squared, 1 plus 1 over N, which gives us, finally, I copy is equal to N times IREF over 1 plus 1 over beta squared, N plus 1. So our error is reduced by a factor of beta. Like I said a couple of minutes ago, the textbook effectively interprets this as kind of an end-all be-all equation, but it's really only valid if we don't mess with the area of our reference capacitor. So let's mess with the area of our reference capacitor and break things, because that's what I like to do. Right? Let's make it harder so that you understand what the hell's going on. That's my goal. So with that in mind, yes. Yes, that is correct. 1 over beta squared. So including this capacitor, transistor QF adds an extra term of beta down here, which is lowering our error since we're dividing our previous error by a factor of beta. So let's say that we are trying to determine the percent error in the mirror currents for the following circuit. If beta is equal to 100. So let's say that this guy has an area of 3. This guy has an area of 5. Let's call this Q2, call this guy Q1, call this guy Qref. This is node X. So I'm just going to identify some currents here real quick that we're going to have to wind up using. We can say this guy right here is ICref. This guy right here is IBref. This guy right here, call IB1. And this guy right here, we'll call IB2. And we are going to use some ideal relationships here to relate our currents I1 and I2 to ICref, okay? So what is our expectation if we were ignoring the contribution of base current to this guy? What should I1 be in terms of IRef? So 3/2, right? That is a 3. That is a 2. So 3/2. ICref and I2 would then be 5/2 ICref, right? That's our starting point, okay? So if we write a Kertal's current law equation at node X, we get IRef is equal to ICref plus IBref plus IB1 plus IB2, right? So all of our currents entering that node X. Using our relationships, then ICref stays ICref. IBref is ICref over beta. IB1 is I1 divided by beta, which is going to look like 3 ICref over 2 beta. And then IB2 is going to look like 5 IC ref over twice beta. All right. So I'm going to factor out a common term, IC ref, and I'm going to express 1 as 2 beta over 2 beta so that I have a common denominator of 2 beta and everything. So it's going to be 2 beta over 2 beta plus 2 over 2 beta plus 3 over 2 beta plus 5 over 2 beta gives me IC ref times 2 beta plus 10 divided by 2 beta. And here is where I can make a choice. Now, it's actually not going to matter remotely, but let's talk about it, right? I want to figure out what my error in my mirror currents are, right? So I'm going to have to put in one of my mirror currents, either I1 or I2, and substitute that relation in for that IC ref right there. The reason why I say it's not going to matter is because we're going to wind up with the exact same error term either way. So just arbitrarily choosing I1, I can say that IC ref is 2/3 I1 times 2 beta plus 10 over 2 beta, and then doing a very tiny amount of algebra, I get I1 is equal to 3/2 IREF times 2 beta over 2 beta plus 10. So this, or really 1 minus this, is the error that I'm seeing in my copy, right? So if I had put in I2 here, this would instead be 2/5, and I would still get the exact same error. So that's why I'm saying it doesn't remotely matter which of those 2 mirror currents I see. I'm going to get the same amount of error in all of the mirror currents, or same percent error anyway in all of the mirror currents. So my copy error then, E copy, is just going to be 1 minus 2 beta over 2 beta plus 10 times 100%. And for beta is equal to 100, this means that I have a 4.762% error, which means my copy currents are 4.762% lower than 3/2 IREF and 5/2 IREF respectively. So that's my error when I don't have that emitter follower in. So let's rework this guy with the emitter follower in and see how low our error falls. We're doing the exact same thing. Determine the percent error in the mirror currents for the following circuit. If beta is equal to 100, that'll work. Oh, actually, I need to give myself more room. I forgot I have to put that other transistor in. So let's drop that guy in here. This is node Y, this is node X, this is VCC. This guy still has an error of, or excuse me, area of 2AE, 3AE, 5AE. Call this guy Q2, Q1, QF, QRef, I1, I2, and I'm just going to be lazy and go ahead and call this guy ICF, since we're making the assumption that IEF and ICF are roughly the same thing. Here's my current IB1, here's my current IB2, here's my current IBref, here's my current ICref, and here's my current IBF. And we're going to start by making the same assumptions we did last time, where we want I1 as 3/2 ICref and I2, right, dummy, 5/2 ICref. So in the idealized case, this is what we would have. Now let's figure out how much having base currents screws everything up. I don't know why that little box is there. Okay, I'm just going to make it go away. Come on, there we go. All right, so same basic thing here, except now we're going to have to apply KCL at both nodes X and nodes Y to develop our relationship, just like we did when we were deriving that equation. So KCL at node X, I have ICF is going to be equal to IBref plus IB1 plus IB2, which is going to be ICref over beta plus 3 ICref over 2 beta plus 5 ICref over 2 beta, and that 5 doesn't look like a very good 5, so I'm going to rewrite that. Factoring out ICref, I get 2 over 2 beta plus 3 over 2 beta plus 5 over 2 beta. And so ICF is equal to ICref times 10 over 2 beta. Where I multiply the first term by 2 over 2 to get a common denominator of 2 beta. Wondering where the hell that came from. If I do KCL at node Y, I get IREF is equal to just ICref plus IBF, right? This current flowing down through transistor QRef and the base current for transistor QF. ICref plus IBF, which is simply ICref plus ICref times 10 over 2 beta. Hold on, I've made them. 10 over 2 beta squared, excuse me, that's what I was looking for, right. So it would be 10 over 2 beta is ICF, and then when I divide that by another factor of beta to get the base current, that's where this beta squared is coming from. So this looks like ICref times 1 plus 10 over 2 beta squared. And now I'm going to substitute in I1. So I'm going to have 2/3 I1 because I1 is 3/2 IC ref times 2 beta squared plus 10 over 2 beta squared, giving me a copy current of I1 is 3/2 I ref times twice beta squared over twice beta squared plus 10, which gives me an error of 1 minus twice beta squared over twice beta squared plus 10 times 100%, or 0.050%. So that's a fairly significant reduction in error. It's actually larger than just having it 1 over beta. So if we screw around with the size of the reference transistors, we can actually have an increased reduction in error by using that transistor QF. So that's not obvious from the way the book does it, so I wanted to show you guys that. All right, so I feel like NPN current mirrors have been beat to death. So let's take a look at Pnp current mirrors, and this will be pretty brief. So most of the amplifiers and all that kind of stuff that we've dealt with to this point, specifically dealing with BJT transistors, have been NPN-based amplifiers, right? So if we wanted to provide a current source as a load for an NPN-based amplifier, we need to do so with a PNP-based current mirror. So generically speaking, a PNP current mirror is going to look a little something like this. Here's Q ref, here's Q1, that arrow should be pointing in. Here's IRef. We have to make sure that our reference transistor is diode connected. And here is I copy. Okay, so pretty much the exact same thing as before, nothing too wild or crazy here. Now, to generate that current IRef would require a separate temperature stable current source, unless we can generate IRef down here at the bottom with an NPN current mirror. So effectively, instead of having multiple band gap reference circuits, one for PNP transistors and one for NPN transistors, we can actually kind of chain our current mirrors together to just work off of a single band gap reference current. So a more practical way to realize this would be something like this. We have our reference current being provided by our band gap reference circuit. We have an NPN transistor, which I'm going to call QREF1. It is diode connected. This is feeding into the base of a transistor Q1. And let me move that actually. See why in a moment. This guy up here, we're going to call Q reference 2. There we go. This guy is connected. This guy is Q2, and this is obviously VCC. And here is our current I copy, and I'm going to call this guy I copy P. Okay. So this looks a little busy, so let me explain what is happening. All right. QRef1 is sensing IRef. Q1 is then copying IRef, and Q1 is acting as the reference current for this Pmos current mirror up top. The problem with this is that we introduced error into our reference for this other current mirror. It's not going to be hugely a big deal. Nathan, what's up? How can I have this same current down here? So for our NP, so we're assuming we're using the exact same band gap reference circuit, which is giving us some current leaving VCC and flowing into something else. I can't have that current leaving my power supply rail and also flowing into ground simultaneously, because then it's just going to be a direct path to ground. So that's why I have to either have to create an entirely separate band gap reference circuit that will give me a current flowing into ground and I build above that, or I start with one, which is what we've been dealing with the NPNs, sense it, copy it, and then use that as a reference for the Pmos. So this gets me out of having to design two different band gap reference circuits, one for Npn current mirrors and another for Pnp current mirrors. But it does wind up introducing a small amount of error. Now, what's interesting about this guy, sorry, this guy should be, not that. Yeah, oh shit, what is going on? Yeah, this guy should be a PNP. Thank you for pointing that out. So I can extend this guy to make more Pmos currents. And I can also actually extend this guy to make more Nmos currents. So this would be a kind of a catch-all. This one current mirror circuit would allow me to make current sources for any NPN-based or PNP-based amplifier stages that I need to have. So that's another particularly good reason why we would do something like this. So real quickly, let's just figure out what the error of such a stage is when all of these transistors have the exact same area. Okay, so our biasing scheme, everything has an area of AE, 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 and I need to relabel this guy Q2. So let's call this guy IC ref, this guy IC1, this guy IC ref 2, so I'm going to make this guy 1, and then this guy here is IC2. So right off the bat, we can observe VBE ref 1 and VBE 1 are the same thing. So IC1 should be approximately equal to IC ref 1. And VBE ref 2 is the same as VBE 2, which means IC ref 2 is equal to IC2, which is equal to I copy P, right? So if we do KCL at node X, so this guy X and this guy Y, we get IREF is equal to IC1 plus IC1 over beta plus another IC1 over beta. So I'm saying that since IC1 is IC ref 1, this is IC1 over beta, and this guy flowing in, the base current for a reference transistor is IC1 over beta, and the base current for our copying NPN transistor is also 1 over beta. Getting confused with all the different transistors all over the damn place. And so this is going to look like IC1 times 1 plus 2 over beta, which means IC1 is IREF times beta over beta plus 2. So we have introduced a little bit of error. Well, this IC1 is serving as the reference for a Pmos or Pnp current source up here. So it should be pretty easy to see that we're going to have, since we have the exact same configuration between these guys as we have here, that's just going to multiply this by another factor of beta over beta plus 2. Does that make sense? We're copying it, so it should be introducing the exact same amount of error. So I copy would then be IREF times beta over beta plus 2 quantity squared, giving us an error of 1 minus beta over beta plus 2 quantity squared times 100% of 3.883%. So roughly 4% error in our Pmos copy current there. The book doesn't discuss whether or not we could put in source followers again. My best guess is we could, but I kind of ran out of time, so I didn't do that. I might do it just for satisfying my own curiosity and then post the notes online or something, but I wouldn't expect that you would have to do anything like remotely like that on the exam. All right, so Pnp and Npn, or I guess Bjt current mirrors, fairly involved, extraordinarily useful. We got 10 minutes left. I legitimately think that's enough time to cover Nmos current mirrors. They're so much easier. So Nmos current mirrors. Let's just get straight to cracking at it. All right, it's going to be pretty much the exact same thing as our NPN current mirrors, except that we're replacing our BJT with a MOSFET. So we have a diode connected. Sorry, there should be MREF. Sensing it, and it is copied by a Nmos transistor here, where I copy is equal IREF if the aspect ratio of transistor 1 is the same as the aspect ratio of the reference transistor. this exactly tells us how we can scale things to get different values as well, right? So if we want our copy current to be half as large, we just double the length. If we want our copy current to be twice as large as our reference current, we double the width. So scaling with Nmos or scaling with really MOSFET transistors is way easier to do than Pmos because it's literally just, we want it to go larger, we may increase the width, we want it to be smaller, we increase the length. Very, very trivial. Notice, since these are MOSFET transistors, we don't have any gate currents to worry about, which means I reference is exactly equal to I copy, unless channel length modulation is involved. The textbook says that including channel length modulation makes things too difficult. I disagree because I have a problem that shows exactly the effects of that. That took less than a page to figure out what was going on, but I'm running out of time, so I might just post this online instead of spending time going over it. So that's an Nmos current mirror. Now let's talk about a Pmos current mirror. So it is the exact same circuit as we had for our BJT Pnp current mirror, except that now we use MOSFETs again. So particularly exciting. So here is IREF. Here is iCopy. And for the exact same reasons, we can get effectively a mixed current mirror where we have a Nmos current mirror serving as the reference for a Pmos current mirror so that we can supply or make copies for any type of amplifier. And that's going to look something like this. Let's see, IREF, MREF1, MREF2, M1, M2. And we're done. In practice, for really stable current mirrors and all that kind of stuff, we would actually wind up cascoding things, but that is apparently too beyond the scope of the textbook that we're using. So that's something to worry about if I don't scare you away from taking 438 in the fall. All right, so that's enough out of me for today. If you have any questions or whatever, I'd be happy to answer them. On Monday, we are going to start talking about differential pair amplifiers, which is really nothing more than two common source amplifiers with their tails tied together. Yes? So what would be So MOSFETs typically can only provide on the order of microamps of current, and BJTs can provide milliamps. That's really the difference. Is the transconductance of a the transconductance of a BJT is typically larger than that of a MOSFET. So you get arguably increased performance, but you also have significantly increased complexity. And that's really about it. It's all down to the transconductance. Somebody
Dr. Hartman.
attempting to say something.
Yeah, I have a question. So for the PNP, we treating the areas the same as in NPN?
Yes,
Yes. Okay. Okay. Thank you.
no problem. Any other questions? Alrighty, I will see you guys on Friday. No, today is Friday. I'll see you on Monday.